Hello and welcome to another CST8216 processor architecture hybrid activity. Today's lecture we're going to investigate series parallel networks, take a look at some definitions and devices, and this will include capacitors. This is an example of a series parallel network where we have a combination of resistors that are in series with each other and in parallel with each other. For example, if we were to have IT coming into the left-hand side of R1, once it reaches the right-hand side of R1, then it would branch off into the three parallel resistors, R2, R3, and R4. But as we have discussed in previous lectures, then at the bottom of those three parallel resistors, the currents would all join together to form IT again and flow through R5. So let's take a look at this in a little bit more depth. It's important to recognize which resistors are in parallel with each other and then what forms the series circuit. So here R2 and R3 and R4 are in parallel with each other because the top of each of the resistors are connected at a common node. Similarly, the bottom of these three resistors are connected together at the bottom node. Therefore, because the tops and the bottoms are connected in this manner, these three resistors are said to be in parallel with each other. Now that we have established that R2, R3, and R4 are in parallel with each other, let's look at the relationship of R1 and R5 in this circuit. Note that only the right-hand side of R1 is connected to the top of the three parallel resistors. In a similar manner, only the right-hand side of R5 is connected to the bottom of those three parallel resistors. So because only one of the terminals of R1 and R5 is connected to the parallel resistors, R1 and R5 are said to be in series with the parallel resistors. So to summarize, R2, R3, and R4 are in parallel, and this parallel combination is in series with R1 and R5. And we've actually seen this before, but not combined like this. We know that in the series portion of a circuit, then the current is the same. And then in a parallel portion of a circuit, the current will branch off into each of the branches of the resistors. And that's true here as well. R1 will contain IT, R5 will have IT flow through it as well. But when IT reaches the top of the parallel combination of R2, R3, and R4, it will branch through those resistors and then recombine at the bottom of the three parallel resistors. What's important for us to do now is write out the general equation for RT as seen by the input terminals. So we have R1 is in series with the parallel combination of R2 in parallel with R3 in parallel with R4, which in turn is in series with R5. Note that I have the brackets around the three parallel resistors, and that's to force myself to remember that that is a parallel branch of resistors. So the first thing I do with the resistors furthest away from the terminals, where I'm actually going to look into the circuit and find out what the total resistance is identify that R3 is in parallel with R4. So I've written that out. Now that we have R3 in parallel with R4, I'm next going to observe that this parallel combination is in series with R2. So I write the equation out for that relationship. And note when I did that I put parentheses around R3 in parallel with R4, just to force myself to remember it's these two resistors here that are in series with R2. So now I want to look at the relationship of R2, R3, and R4 with respect to R1. And I will note that R2 in series with the parallel combination of R3 and R4 is in parallel with R1. So I can build up the equation even further as shown. In summary, R3 and R4 are in parallel. Their parallel combination is in series with R2. And this resulting combination is then in parallel with R1. So we've discovered the relationships, we've identified the elements which are in series and the elements that are in parallel. And now we can write the equation for RT starting at one of the terminals. So the total resistance is equal to R1 in parallel with the combination of R2 in series with R3 in parallel with R4. So let's try this again, except this time we'll actually use some resistor values. All the resistors are going to be in ohms, and you can see that I have marked the resistor value right beside the resistor. So for example, the 7 beside R1 means that R1 is equal to 7 ohms. So I start with my equation that I developed before, where I have RT is equal to R1 in parallel with the combination of R2 plus R3 in parallel with R4. So I start at the very right hand side of the diagram, and I have R3 in parallel with R4. So inside the big equation there, where I have R3 in parallel with R4, I substitute the values. So what I'm going to do is work along here and collapse this equation from right to left. So I have my 6 ohms in parallel with 6 ohms, which gives me 3 ohms. And then we said that that parallel combination of R3 and R4 is in series with R2. So therefore I have 3 ohms plus 4 ohms, and that's 7 ohms, which is in turn now in parallel with R1. So 7 ohms in parallel with R1's value of 7 ohms results in RT being equal to 3.5 ohms. And that's how we collapse the formula from the right to the left to solve for RT. Okay, so I'm going to do this one more time, but this time I'm going to do it graphically. So here's the given circuit, and what we want to do is we want to find RT. We start at the furthest distance from the terminals where we want to find RT from, and here we discover that we have the parallel combination of R3 and R4, and that's equal to 3 ohms. So now what we do is we replace R3 and R4 with the equivalent resistance which we just calculated, which in this case is 3 ohms. Now we can very easily see that the 3 ohm resistor is in series with the 4 ohm resistor. So we get the equivalent resistance of those two resistors in series, which is equal to 7 ohms. Once again, we redraw the circuit and we insert the newly calculated equivalent resistance of 7 ohms. Now we observe that the two 7 ohm resistors are in parallel, so we find out the equivalent resistance of those resistors, which turns out to be 3.5 ohms. Finally, we draw the single resistor that represents the total resistance of the series parallel combination circuit that we just solved. So that's how we can take a series parallel combination circuit and break it down into a single value of equivalent resistance, the total resistance, using graphical methods. So whenever we analyze a series parallel circuit to find out, say for example, VR3 or IR4 or the power in a certain branch, there's a couple of things that we should always remember. No matter how complex the circuit is, the same current will always flow through series elements, and the same voltage will be across all of the parallel elements. So Kirchhoff's voltage law and Kirchhoff's current law are always valid, regardless of the parallel or series configuration of the circuits. And there's also some additional notes here, which I'll let you read, which we've basically gone through in the last few slides. Let's try and analyze a simple series parallel circuit now. In this example, what we're going to have to find is the total resistance, the three currents, I1, I2, and I3, as well as V1 and V2. So let's try this now. We can't calculate V1, V2, I1, or I3 unless we know what the total current is, I1. And before we can do that, we have to find out what the total resistance is. Once we know that, then we can calculate the total current. So what I'd like you to do now is write out the general equation for RT, and then see if you can solve this circuit for the total resistance. Give that a try now. Here's the type of calculations you should have come up with. You should have written out the general equation for RT, which is equal to R1 plus the parallel combination of R2 and R3, plugged in the values, solve the equation, and then come up that RT was equal to 20 kilo ohms. So now that we've found RT, we're ready to calculate the total current in the circuit. So take a moment and see if you can do that. The total current in this circuit, denoted by I1, which we can also call IT, is equal to the total voltage divided by the total resistance. So here we have the total voltage equal to 48 volts, and we previously calculated that the total resistance was equal to 20 k ohms, so that gives us a total current of 2.4 milliamps. So I1, also called IT, is equal to 2.4 milliamps. Now that we have calculated what the total current is, we note that this total current goes through R1. So now we can calculate the potential difference across R1, or the voltage across R1. So give that a try now. So the voltage across R1, which is denoted as V1, works out to the total current times the value of R1, which is equal to 2.4 milliamps times 12 kilo ohms, which equals 28.8 volts. Hopefully you got this value. If you didn't, go back and do it again. Now that we know the value of V1 and we're given the value of the total voltage, we should very easily be able to calculate the value of V2. Let's see if you can come up with that value on your own. The easiest way of calculating V2 is to take the total of the applied voltage and subtract the value of V1, which we just calculated. Therefore, in this case, V2 is equal to 48 volts minus 28.8 volts, or V2 is equal to 19.2 volts. Now we'll just do a quick check and employ Kirchhoff's voltage law, which states that the sum of the voltage drops is equal to the applied voltage. And here we show that V1 plus V2 is equal to the applied voltage of 48 volts. So we're okay to go on now. Now that we know that there's 19.2 volts across both R2 and R3, it should be very easy to calculate both I1 and I3. Go ahead and try I2 now. So I2 is equal to V2 divided by R2, and that's the current that's flowing through that 10k ohm resistor. So we end up with 19.2 volts divided by 10 kilo ohms, which is equal to 1.92 milliamps. That seems like a reasonable answer because its value is less than IT. So let's go on and calculate I3 now. I3 won't be that big of a current because the total current is equal to 2.4 milliamps, and that total current branched out at node B, and 1.2 milliamps of it went through as I2 through the 10k ohm resistor. So let's calculate I3, which is the current through R3, the 40k ohm resistor. Do that now, please. So I3 is equal to V2 divided by R3, and that works out to 0.480 milliamps. Now, you might have written that as 480 microamps, and you wouldn't be wrong. The reason I wrote it as 0.480 milliamps is that because eventually I'm going to have to add I2 plus I3 to make sure that it comes up to IT. And since IT is in milliamps and I2 is in milliamps, I chose to leave I3 in the same units. So now we're all set to confirm Kirchhoff's current law, which states that the sum of the current entering a node is equal to the sum of the current leaving the node. So here we want to prove that I1 plus I3 is equal to IT. So we add the 1.2 milliamps to the 0.480 milliamps, and we should come up with IT is equal to 2.4 milliamps. If you didn't get that value, try your calculation again. As a summary to this problem, we were asked to find the total resistance, the currents I1, I2, and I3, and determine the voltages V1 and V2. The thing I'd like you to note here is that although we were asked to do those things in an apparent order, RT, I1, I2, I3, V1, and V2, that's not how we actually found those values. The first value we found was RT, and then we found IT, or R1, and then we calculated V1 and V2. Finally, we calculated I2 and I3. So, although we were asked to do things in a certain order, it didn't make any sense to actually try and find those values in that order. It was much easier for us to go through the circuit in a piecemeal manner and do things in order of the way that the circuit was laid out. So I hope this makes sense to you, and I would suggest that you try this circuit again on your own. Maybe even try different values and see if you can come up with the correct solution. Just remember that Kirchhoff's voltage law and Kirchhoff's current law will determine whether or not you have the correct solutions. So let's move on to a different topic. I'd like to go back to a discussion about our resistors again, because we've already looked at resistance. We built circuits in Multisim where we had a power supply which supplied voltage and current to a circuit. We looked at series circuits, we looked at parallel circuits. But I'd like to look at it from a different perspective now. And I'd like to look at the resistor as a linear device. And in a linear circuit, current is proportional to voltage. Let's look at this a little bit in more detail. So if we set up a small circuit in Multisim like this, and we held R1, in the case of the top diagram, constant, and we increased the value of V1 by using a variable power supply, we would note that the current linearly increases as the applied voltage increases. And you can see that in the first one with R1 equal to 10 ohms, where if we have 10 volts applied, then the current is equal to 1 amp. If it's 20 volts applied, it's 2 amps. 30 volts applied, 3 amps, and so on. The same thing would apply in the second circuit. This time we've increased the resistance, so from Ohm's law, V is equal to IR, then we would suspect that if we increase the resistance, then we would see less linear current, and that is the case. We notice that when it's 10 volts applied, we've only got a half of an amp. 20 volts applied, we've got 1 amp. 30 volts applied, we've got 1.5 amps, and so on. So the resistor is a linear device. Another way that we can prove that a resistor is a linear device is if we were to measure its resistance. And in the top diagram, I have the positive lead of the ohm meter to the left-hand side of R3 and the negative lead to the right-hand side of R3, and the resulting resistance is 20 ohms. Note that in the bottom diagram, I reversed the leads on the ohm meter, but the resistance is identical, 20 ohms. So when measuring the resistance of a linear device, the results will be the same regardless of the polarity of the instrument's leads. This brings me into the topic I really want to talk about now, which is nonlinear devices. These devices have to be measured in a certain manner, polarity does matter, and current and voltage are not proportional in nonlinear devices. We're going to talk about a couple of devices. One of them is a capacitor, and I've shown you here what a capacitor looks like, different sizes, and I've also introduced you to the notion that the voltage E across a capacitor is not linear with respect to time. So let's take a look at some other nonlinear devices and then introduce the capacitor in a more formal manner. A light-emitting diode is another example of a nonlinear device. We saw a light-emitting diode, or LED, in lab number 1, as depicted in the circuit on the left. When the counter reached 9, then the LED illuminated. So let's look at some characteristics of an LED. It's a semiconductor device that allows current to flow in only one direction. And if the anode is approximately 1.5 volts greater than the cathode, as depicted below, then current flows and the LED illuminates. So here's an example of an LED circuit. We haven't built this in the lab because this U2 there is it's a virtual LED, but you can find that in the virtual components if you wanted to experiment with this. So on the left-hand side, I've just drawn a simple schematic diagram with a switch in it, and if the switch is open, of course, there's no current flowing, so the LED does not light. But if I was to close the switch, then we would have current flowing through the switch, through the 470 ohm resistor, and through the LED. Now that's the diagram on the left. Now the diagram on the right, it's the same thing. It doesn't matter where the switch is. In this case, I put the switch closer to ground, but the switch still controls whether we have an open circuit, where there's no current flow, or whether we have a closed circuit with current flow. Now the interesting thing between these two diagrams, or the observation that I'd like you to make, is that On the left-hand diagram, if the switch is open, then the voltage at the switch, the right-hand side of the switch, or the left-hand side of the 470 ohm resistor, is equal to 0 volts because it's an open circuit. But the circuit on the right is slightly different configured, and the voltage on the right-hand side of the switch, or the left-hand side of the LED, will be equal to 5 volts. Because it's an open circuit, there's no current flow, and therefore the full potential of VCC is felt on the right-hand side of the switch or the left-hand side of the diode. That's an important observation to make. Now let's get back to our discussion about current. I've closed the switch, and now I have current flowing from VCC through the switch, through the 470 ohm, and through the LED, and that's on the left-hand circuit. The same sort of thing on the right-hand circuit. We're going from VCC through R1, through the virtual LED U2, and through the switch. In both cases, regardless of the configuration, the current through the diode, which is annotated as ID, is equal to VCC divided by R1. Recall that the purpose of that 470 ohm resistor is to limit the amount of current through the LED. After all, we don't want the LED burning out, but we have to pick the resistance in such a manner that there is current, sufficient current flowing through the diode so that it illuminates. In this case, we have 10.6 milliamps flowing through the diode, and if we were to look at the manufacturer's specification about a certain diode, it would tell us how much current we need through the LED in order for it to illuminate. It would also tell us what the minimum current would be, the optimum current for power conservation, and the maximum current where we would then see smoke coming out of the circuit and the LED would fry. Then it would be an open circuit and there would be no current flowing. Another example of a nonlinear device is the transistor when used as a switch. Basically what we have here is on the left-hand side some sort of digital logic gate which has an output of 5 volts. But this 5 volts is not enough to drive or turn on some other device. So we need an electronic switch that can supply current, sufficient current, to a device to turn it on and off. So in this case, we're going to use a transistor. And the concept here is that if the transistor has a positive value on its base, which is the lead denoted as B on the transistor at the right-hand side, then the transistor will turn on. And when the transistor turns on, it acts like a switch, and then current can flow through from the 12 volts through the current limiting resistor, through the LED, through this transistor or switch, and then it completes its path to ground. And that's basically how we use a transistor as a switch. Let's look at another example. So one of the things that we have to remember when we use a transistor as a switch is that it must either be off or fully on. And when it's fully on, the transistor is said to be saturated, and it acts like a closed switch. So there's going to be maximum current flow. And when it's off, it's going to act as an open. So we have an open switch, and there's no current flow at all. If you wanted to see how this worked, then you could build the following example circuit in Multisim. Here we have a transistor, which is denoted as Q1, acting as an electronic switch. As shown with SW1 in its current position, the transistor is off. That's because there is not a positive voltage on the base, the B input of the transistor. So there's no current flow in this circuit whatsoever. However, if I was to move the switch to the upper position, then what I would effectively be doing is turning on the transistor because there's a large potential difference on the base compared to the emitter. So I have turned on this electronic switch, and now there would be current flowing from VCC through the diode D1, through R1, through the transistor Q1, and down to ground. So the LED would be illuminated. Here's another device that we've already seen in a previous lab, and that's a capacitor. And capacitors are another fundamental building block in electronic circuits. They come in all different shapes and sizes, all different voltage ratings, and let's take a look at these in a little bit more detail as well. So if we were to look at a basic construction of a capacitor, it will consist of two conductors called plates, separated by an insulator called a dielectric. On the right hand side we also see the symbol for a capacitor, which is what we've seen in previous labs. So let's take a look at this in some more detail. When we talked about resistors, we found out that their unit of measure was the ohm. But when we talk about the unit of measure for a capacitor, it's the farad. And generally, values for a capacitor are in the sub-farad range. Typical values that you might see are 27 picofarads, 0.05 microfarads, and so on. When we were creating a simple circuit in Multisim, we saw some bypass capacitors up in the upper right-hand corner of the schematic capture. And their purpose was to filter any ripples in the DC voltage that was in the circuit to ground. And here's an example of the capacitor as a filter. What I have here is a power supply that converts the AC voltage coming out of the wall into a DC voltage that we would use, say for example, in our computer. We have on the left hand side the voltage in time, and you can see that's an alternating sinusoidal, just like we took an MET 8100. It goes through something called a rectifier, which has some diodes in it, and it half-wave rectifies the signal so that we only get the positive sides of this sinusoidal, and then it goes through a filter capacitor, and you can see that the waveform is starting to be smoothed out, but it needs a little bit more help. So what we do is we put some sort of a voltage regulator that will regulate the outputs to a specific value, say for example 12 volts or plus 5 volts. But coming out of there, it'll have the smallest little amount of ripple as well, and we don't want any sort of fluctuations of that DC voltage. So what we're going to do is we're going to put an output capacitor there, which will smooth out that voltage so that there is little or no fluctuation in that DC voltage. So what do I want you to remember from this portion of this lecture? I want you to remember that we can use a capacitor as a filter. So in concluding our discussion about capacitors, I'd like to say that capacitor charging is a nonlinear function. With resistors, we found that the current and the voltage were both linear. As you increased the voltage, holding the resistance constant, then the current increased in a proportional manner. But that's not the case with capacitor charging. Capacitor charging cannot change, or the voltage cannot change instantaneously. It begins as 0 and exponentially increases to E volts as shown in this diagram. So you can think of a capacitive circuit in this case being the integration function. So that's where we're going to leave capacitors in CST 8216 processor architecture.